Okay, so significant digits. This will be with you forever. You should have been exposed to them in physical science 2 years ago. You're going to get them now, and you're going to get them in physics, and then any other science classes that you take in college, they will matter. The main idea here is we want to make sure that we are only we're only expressing a degree of accuracy in our answer, which reflects how accurate we were in our measurements. So if you measure with a tool that only goes to a certain number of digits, you don't want to express an answer that has more digits than that, because then people reading your results will say, oh, this person has some super amazing ruler that goes to 10 millionths of a meter. No, you don't. And so you want to make sure that your answer is only as significant as your measurements. So the rules, it's very simple. Leading zeros are never significant. If you have a 0 before non-zero digits begin, they never count, even if there's a decimal point. If it's 0.0000625, you only have 2 significant digits. The 625, right? None of the zeros before matter. So leading zeros are never significant. Trailing zeros are only significant if there's a decimal in the number. So 206.003000, the last couple of zeros there, are significant if there's a decimal point. So trailing zeros are only significant if there's a decimal in the number. So the number 600, 600, if there's not a decimal point, there's only one significant digit, the 6. 600 points, there are 3 significant digits, 600. Okay, so even if there's not any placeholders after the decimal point, if there's a decimal point, then the trailing zeros matter. The trailing zeros are significant. Okay, all non-zero digits and zeros between non-zero digits are significant. So 1003 has 4 significant digits: the 1, both zeros in the middle, and the 3. Okay, so those are the rules. Your book makes a bigger deal out of it, and it takes more verbiage to describe it, but this is the essence of significant digits, and it's a lot easier if you just remember this one. There's a song that you can listen to that does a really good job. It says, I don't know what the melody is, but the lyrics are.
A measurement, what makes it significant?
There you go. Thank you, Alan. So,
Numbers that you measure.
all the ones that you should treasure. Yes. Okay. And there's another song. I forgot about that one. There's another song that says that the lyrics are leading, never, sandwiched, always, trailing, dot yes, no dot no. And that's basically these laws as well. So whatever helps you stick this in your head, you're going to need to use this a lot. So in the number 365, there are how many significant digits?
3!
3, yay! 3 sig figs, isn't it exciting? And in the number, come on mouse, there you go, in the number under my video, well, that you couldn't read.
2. There's 2.
There's 2. Somehow the other, there it is, 1200.
4. There's
1200 had 2
4.
significant figs. No,
4.
1200 had 2. Because chaos, not okay. There's no decimal point here, so just the 1 and the 2 are the only 2 significant digits. Let's see if I get these.
4.
4 sig figs.
There you go. 4 sig figs, because now I have a decimal point. Okay, and so now the two zeros afterwards matter. That one, raise your hand.
3, 1.
That one, raise your hand. Shanice has her hand up, but now Justin does. Yes.
I'll let.
Okay, go Shanice. 3. No, I'm sorry. That's not
4. 1.
1. Leading zeros never count. Leading zeros never count. So even if there's a decimal point, leading zeros never count. So that's just 1. Oh, but this splash says 3. The splash is wrong. There's only 1. Leading zeros never count. Leading zeros never count. Okay. 10.003. Mr. Lavilla.
5.
5 is correct. Because now these zeros are sandwiched between non-zero numbers. So now I have 5 significant digits. Yay. Do I have another one? Yes, I do. How many significant digits there? 4 is correct. 7392. These guys are just placeholders. Trailing digits only count if there's a decimal. Sorry, trailing zeros only count if there's a decimal. Okay, 4 is correct. Mr. Oz?
7.
7 is correct. Because all of these are measured zeros if there's a decimal point. If this person measured and only got 6 and didn't measure the rest of these places, they should have just put 6. But when they put point and 6 zeros, they're telling you that they measured out to 6 decimal places. Okay? So 7 significant figures. There you go.
Mr. Alley,
That's me.
I think your board is too white because the video's not.
So a good way to express significant digits is in scientific notation. You guys have seen scientific notation before. You guys have done this with physical science, and we even did, I think, a little significant digits with biology a few times, but not as much. So here we have a way of expressing numbers where we only put the significant digits down. We only write those numbers. And so that makes it really easy when you are reading somebody's work to see what was significant and what was not. You don't have to guess. They're only going to give you the significant digits. Okay? You write it as a decimal value with only 1 digit to the left of the decimal point. So something point and then however many more numbers you need, followed by 10 to the n, where n equals the number of places the decimal was moved. Have you guys seen this before? Does this ring bells? Okay, good. I don't have to teach this to you. This is a reminder thing. So let me show you some numbers. So this 1,458,000, that has 4 significant digits. And if I were to write that as a scientific notation, Renee, what would I put? How would I turn that into scientific notation? Well, what would be the number? 1.458, right? You only write the significant digits. 1 times 10 to the what? 6. Because if I put the decimal point here, I will have to move it 1, 2, 3, 4, 5, 6 times to make the number reappear, right? So 1.458 times 10 to the 6th. Only 4 significant digits. And so I want to express 1.458. And then the decimal moves 6 places. And so my answer is times 10 to the 6th. And does everybody see how that happens? Amen, he says. All right. What's your question, Alex?
Oh, no, I'm ready to answer.
Bueno.
I got it.
Okay. 17, what is that? Hundreds, thousands, millions, billions, trillions. 17 quadrillion, 362 trillion. That's the number.
I got it.
Okay, what is it? What is it?
1.7362 times 10 to the 16th power.
Times 10 to the 16th power. 3, 6, 9, 12, 15, 16. That's correct. 5 significant figures, 1.7362.
Every day is math.
Moved 16 places. Okay, moved 16 places, so times 10 to the 16. Okay?
It's really good. Really good. Really good.
Oh,
really?
Celeste, how would I express that number in scientific notation? Hold on. Celeste's going to do this for us. How many significant digits first? 2.
So 2.4 times 10 to the
2.4 moves 6 places, so times 10 to the negative 6. Good job, good job, good job. Okay, Uno Mas.
Alex. I got it.
No.
We're
gonna let Cody.
Oh. Cody, step up. Cody,
1.9655 times 10 to the, wait, let me count. 17.
Good.
Yeah.
job.
Cody.
And Haley.
I can't. The zeros are blurry.
Okay, 1, 2, 3, 4, 5, 6, 7 zeros before 2, 1, 4, 5.
So 2.
No, you did.
Wait, 1, 4, 5. How many zeros?
7 zeros.
Times 10 to the 8.
Not times 10 to the 8.
What? Negative 8.
Times 10 to the negative 8. Right, because you're going the other direction. There you go. That's scientific notation that will help you with your sig figs. Alrighty.
There's my mouse. There's my mouse. Oh, mousey.
So when we're doing this, it's an opportunity to be honest. That's why we do this. You want to make sure that the measurements that you express in your answer show the reader how good your measurement tools are, and that you don't show a whole bunch of digits when you didn't measure a whole bunch of digits. So you need to make sure that you express your answer in the least accurate measurement that you had. So for addition and subtraction, it's just like adding decimals anyway, where you line up the decimal place, you do the math, and then you round to the least number of decimal places that you had. So if you're adding 3.25 and 6.4, the 0.25 and the 0.4 add up to 0.65, but you don't say 0.65 because you, in one of your measurements, you only had 0.4. So you would round to the tenths place, right? You want to only show as many decimal places as your least accurate measurement had. And so you don't express the maximum number of decimal places. You express the minimum number of decimal places, depending on the numbers that you have or subtract. Okay, so a quick example of that, if I'm adding 101.25 and 3,536.2, if you do the math, and 123.448, you do the math and you get 3 decimal places because, you add these up and there's 3 decimal places here, so this 8 comes down. But if I were to just express the answer this way, the reader would say he knows the answer out to the thousandths, sorry, the 10,000ths place. Thousandths place. There you go. I know my places. There you go. But I don't, because in this particular instance, I only measured to the tenths. And so I need to be sure to tell my reader that at one point I only knew out to the tenths. So I need to express my answer only to the tenths. Okay? So then you would express 3,760.9. Okay? So that's how you do this with addition and subtraction. For multiplication, you round to match the number of sig figs in the least accurate number. So it doesn't matter where the decimal point falls, like it does for addition and subtraction. For multiplication and division, you just round to the least accurate number that you have. So if you have 3 sig figs in your least accurate number, then you express your answer in 3 significant digits. If you had, 5 significant digits, you'd express your answer with 5 significant digits. Okay, so just another example of that as well. See your pen still moving. Round to the least accurate number. Oh, and 2 more ideas here. Conversion factors don't affect it. So conversion factors don't affect it. So if I have a number that I've measured, and I've measured it in meters, and then I need to turn that into some other unit of measurement. Let's say for some crazy reason I need it in inches, and I look at the conversion factor for how many inches are in a meter. That conversion factor does not come into play for sig figs. So I wouldn't care how many significant digits my conversion factor has. I would only care about the significant digits of my measurement. Okay, so measurements are the only thing that you put into the mix. And then don't round until the end, because if you round after every step, you're going to introduce rounding errors, and your final answer will be off because you rounded in the middle. Do the math with as many digits as you have, and then in the very, very, very end, round your final answer to the right number of significant digits. Okay, so I have some examples. wants to populate? Come on. Come on, make me happy. No? You're not making me happy? Yeah. What's going on? That's not the end of it. It is the end of it, but I'm supposed to have examples. My examples died.
No.
Okay, well, let's just do some examples then. We can overcome. We can be smarter than technology. So, you're doing density calculations this week. So let's say that we're doing a density calculation of an object, and it weighs, we find out that it weighs 3.21 grams, and we're happy with that. Density is mass divided by volume. So now our volume, we take a volume measurement, and we get 6.2 cubic centimeters. So density is mass divided by volume. Ooh, volume, that's V. There you go. And so I need to do 3.21 grams divided by 6.2 cubic centimeters. And somebody with a calculator will do that for me. It's about a half. 3.2 divided by 6.2? No, other way around. 3.21 divided by 6.2 will not be 1.5. It should be about 0.5. 0.51774. Okay, and that's grams per cubic centimeter. But 0.51774 has 5 significant digits. And in this answer, or in this measurement, I had 2 significant digits. And in this measurement, I had 3 significant digits. So 3 significant digits and 2 significant digits. My least accurate measurement was 6.2 with 2 significant digits. So I have to express my answer as 0.52 grams per cubic centimeter. Okay. That's what we're doing. So for addition and subtraction, you just line up the decimal point, multiplication and division, do your multiplication and division, and then round to the number of significant digits that your least accurate number have. Okay, let's do one more with unit conversions, just so you can see conversion factors don't come into play. I'm going to go, let's say I measured something, the only thing I had was an English tape measure. So I measured something, and it was 6 feet 3 inches tall. Okay, and I want to know how many centimeters is that? 6 feet 3 inches tall. Well, 6 feet is 72 inches, and 3 more would be a total of 75 inches. Okay, and then I need to turn that into centimeters. So 75 inches, and there are 2.5 centimeters. Actually, 2.51 centimeters per inch, right? So if I multiply 75 by 2.51, somebody with a calculator, help me out, it's 170 something. 75 times 2.51. 188 point what? Okay. Centimeters. So I had 2 significant digits in my 75 inches. I had 3 significant digits in my conversion factor. Conversion factors do not influence significant digits. So I only go with the significant digits in my measurement. So I would have to say 190 centimeters. Okay? Everybody understand? Renee Wimper, do you understand? Okay. Are there any questions from anybody? All right, there you go. So that is the gist of what we're going to be doing in this last part of the chapter.